7.12 Practice Problems. A saturated aqueous solution of cadmium fluoride is prepared. The equilibrium in the solution is represented above. In the solution, the cadmium ions have a molarity of 0.085 molar, and the fluorine ions have a molarity of 0.117. Some 0.9 molar sodium fluoride is added to the saturated solution. Which of the following identifies the molar solubility of the cadmium fluoride in pure water and explains the effect that the addition of sodium fluoride would have on its solubility? So this was at a saturated solution, and we have 1 cadmium per cadmium fluoride. So this was the original molarity of the cadmium fluoride. So that is the initial molar solubility of the cadmium fluoride compound. And after we have added sodium fluoride, that means that we're going to have an excess of fluorine ions suddenly within the solution, which will push my reaction back toward my initial undissolved cadmium fluoride, because I have too many fluorine ions, so it will push it back to precipitate out some of the fluoride and get some just cadmium fluoride solid back. So we're going to compare here. So I've already eliminated the 2 answer choices that don't match the molar solubility of the cadmium fluoride originally, because again, the cadmium fluoride molarity should match that of the cadmium, since there's 1 cadmium per cadmium fluoride. And A says that the molar solubility of cadmium fluoride in pure water is 0.585 molar. And adding sodium fluoride decreases this solubility because the equilibrium shifts to favor the precipitation of some cadmium fluoride. This is true. Again, we have too many fluoride ions, so we are going to precipitate out some cadmium fluoride. Option B says the molar solubility of cadmium fluoride in pure water is 0.0585 molar. And adding sodium fluoride has no effect on solubility because it only changes in temperature can increase or decrease molar solubility of an ionic solid. That is not true. Temperature can affect solubility, but so can having more of the same ion appear. So option A is going to be my answer choice. Shown above is the chemical equation for the dissolution of the slightly soluble salt copper 1 bromide. Its KSP value in pure water is experimentally determined. Copper 1 bromide was found to be much less soluble in a 0.001 molar sodium bromide solution than in pure water. Which of the following correctly explains the decrease in solubility for copper 1 bromide in the 0.001 molar sodium bromide? So sodium bromide is going to be very readily soluble since we are bonded with an alkali metal, and so we are going to have an increase in bromine ions that are present within the solution of sodium bromide, thereby pushing back toward the solid copper 1 bromide. So we are going to find an answer choice that matches that, basically. A says the concentration of water is much less in the sodium bromide solution than in pure water, reducing the rate of dissolution. The concentration of water is not the determining factor. The thing that is pushing us left or right is going to be having repeat ions, common ions. So A is not going to be our choice. The presence of sodium ions in the saturated solution inhibits the dissolution of salts. Nope. Sodium is not a common ion, and so that is not going to have any effect. The presence of additional bromine already in the solution decreases the value for the KSP of copper bromide, causing the solubility to decrease. So it's not going to change the KSP of the sodium bromide. Instead, it's going to push our equilibrium toward more of the solid, undissolved copper 1 bromide. So option D says the presence of additional bromine ions already in the solutions mean equilibrium will be reached when much less copper bromide has been dissolved. Again, we're going to have a concentration of bromine that is much higher, and therefore we will reach the KSP of the C of the copper 1 bromide a lot faster. So answer choice D is going to be my choice. Shown above is the information about the dissolution of silver chloride in water at 298 Kelvin. In a chemistry lab, a student wants to determine the value of S, the molar solubility of silver chloride, by measuring the concentration of silver in a saturated solution prepared by mixing excess silver chloride and distilled water. How would the results of the experiment be altered if the student mixed excess silver chloride with tap water, in which chlorine has a concentration of 0.010 molar instead of distilled water, and the student did not account for the chloride already in the tap water? So if we were to increase the concentration of the chloride ion, then we are going to decrease the overall amount of silver that is going to be able to dissociate, because we will have too much chloride. So we will shift the reaction back to having the too much silver chloride. So our overall KSP, our overall solubility, will look a lot smaller just because we weren't able to dissolve as much silver chloride as we should have been able to dissolve. And so we're going to eliminate any choice that says that the KSP would be too large, that's answer choice C, or that it's not going to be altered, that's answer choice D, because again, we're not going to be able to dissolve as much silver chloride, and therefore we will have a smaller KSP than expected. So answer choice A says the value obtained for KSP would be too small because the chloride ions would be attracted to the silver ions in the silver chloride crystals, thus preventing water molecules from reaching the crystals. No. The chloride ions are going to shift our equilibrium because the concentration is going to be already too high in the system overall to allow for the silver chloride to dissolve. Answer choice B says the value obtained for the KSP would be too small because less silver chloride would dissolve because of the common ion effect due to the chloride already in the water. That was the statement that we basically had already predicted as our answer, and so that is going to be the answer choice that we are going to select. Answer the following questions about the solubility of silver chloride. The value of KSP for silver chloride is 1.8 times 10 to the negative 8th. So first up, we're going to calculate the value of the concentration of silver in a saturated solution of silver chloride within distilled water. So we know that our KSP is going to be equal to the concentration of the silver multiplied by that of the chlorine. Both of these are in equal proportion there, so we can just go ahead and say that the KSP is going to be equal to x squared, since these values are going to be the same. And then our KSP was stated as 1.8 e negative 10, and that is equal to x squared, so square root of both sides. Gives us 1.3 e negative 5 molar as our concentration for the silver, or the concentration for the chlorine, since again those are both going to be the same value. The concentration of chloride in seawater is 0.54 molar. Calculate the molar solubility of silver chloride in seawater. So we are going to go ahead and say that S is going to be equal to our concentration of silver times our concentration of chloride. Our S here is going to be equal to the KSP, so that's going to be 1.8 e negative 10 still, times the concentration of silver. And then we have the concentration of chloride given already within the system of 0.54. So if we divide both sides by the 0.54, that will give us 3.3 E negative 10 molar with correct sig figs. Explain why silver chloride is less soluble in seawater than in distilled water. So we can see that we have a much higher concentration of silver that would be able to be dissolved within just distilled water versus a much, much lower concentration of the silver that would be able to be dissolved in seawater. We have it being less soluble because of the common ion effect. With chlorine already present, is going to reduce the amount of silver chloride that could be dissolved. And that's it.